Hi, everybody. So now let's take up the next step in the proof of the classification of finite abelian groups, and that's a result that tells us about the structure of finite abelian p groups. So remember that a finite abelian p group is a finite abelian group whose order is a prime power. And what we're going to show is that a finite abelian p group is actually a product of cyclic groups, abelian groups of prime power order. And the way we're going to do that is by a kind of a splitting result. So we're going to take our group G, and we know that every element in that has prime power order. And we're going to take one which has the biggest possible prime power order. So if your prime was, say, 7, then there might be elements of order 7, there might be elements of 49, and there might be elements of order whatever 7 cubed is. And we're going to take an element of order 7 cubed. And we're going to show that you can split off the cyclic subgroup generated by that element in the sense that you can recover G as a direct product of this cyclic group and a remaining subgroup H. And then what you do is you take this H and you repeat this argument, and it's split off another cyclic group, and you keep splitting it off until the group that's left is cyclic, and then you're done. And this is another inductive argument that works with H and G mod H. And we're going to again assume inductively that, that our result is true for groups G of order less than n. And then we're going to use that to have the result for H and G mod H, and then from that move to G. So let's take our G of maximal order. If that element generates G, then G is cyclic and we're done. So, because we can take H to be the trivial group. So what we're going to try to do now is we're going to try to find a subgroup of G of order P which doesn't intersect the cyclic subgroup generated by G. And so now we're going to be able to look at G, and on the one hand, we're going to have this cyclic subgroup H, and on the other hand, we're going to have this quotient group G mod H. And our goal is for the coset GH in G mod H to have the same order as G in G. Now, then what that tells us is that since G mod H is small, so H is going to turn out to have order P. So what that's going to tell us is that by induction, we can split G mod H as the cyclic subgroup generated by GH and some other subgroup, which we don't know what it is. And from that, we're going to show that you can reconstruct, I guess maybe the best word would be to lift these things back. This subgroup is really a subgroup of the factor group. You can find a subgroup in G, which when you mod out by H gives you this decomposition, and then that subgroup is the one that you want. So that's more or less the strategy. I've kind of given away the whole punchline, but let's work our way through it now. So if n is 1, so here the induction is on, so the order of G is p to the n, and we're going to assume that if order of G is p to the k for k less than n, then the result is true. So if n is 1, if the order of G is P, then G is cyclic, so we're done. And we can take H to be the trivial group. So we get our product decomposition. So now we're going to let G be of maximal order among the elements of G, and so its order is a power of P. And one thing to observe is, because this is the largest possible order, if you take any element of the group and you raise it to this power, you have to get the identity. Because if you didn't get the identity, you could find an element of even bigger order. So That's one of the nice things about this maximal order. And once again, if this particular group G generates G, then it's cyclic, and we're done. So we're in the situation now where we have an element of maximal order, but it doesn't generate the group. And if you want to think about what's going on, think about a group like Z8 cross Z4. So this is an abelian 2 group. The element of maximal order would be an element of order 8, like this one. This has an element of order 8. And it doesn't generate the group. So in a certain sense, you can think of this element here as the G that we would have picked if we were doing the proof for this group. So we're assuming it's not cyclic. So since it's not cyclic, this is a typo here. We look at the quotient group, G mod the cyclic group generated by this element G. And in this case, we take an element of minimal order bigger than 1. So in other words, we're taking an element. I mean, I guess this wasn't really a typo. This is just confusing. This is actually a coset. So we're going to choose the coset A in this quotient group, which is of minimal order greater than 1. And this A is not in the cyclic group generated by G because this is a non-trivial coset. It's of order greater than 1. And it has to have order P, because if it had order P squared, for example, then we could raise it to the Pth power and we would get something of order P. So the coset AG, if it has minimal order, must have order greater than 1. It must have order P. This is similar to what we did in the other proof. And so we get an element A, so that A to the P is in the cyclic subgroup generated by G, but A is not in the cyclic subgroup generated by G. And now what we're going to try to do is to construct an element of order P. It's very similar to the calculation that we did before, but we don't have the situation where the subgroup and the group itself have relatively prime order. Everything is a power of P in this case. So the statement that A to the P is in the cyclic group generated by G is the statement that A to the P is a power of G. That's what this statement means. And if you now raise, remember we know that any element has to be the identity. So if you raise A to the P to the M minus 1, that has to be the identity because it's A to the P to the M, but it's equal to G to the R to the P to the M minus 1, which is G to the RP to the M minus 1. And if this power of G is the identity, then the power has to be divisible by the order, right? If G to the something is the identity, then that tells us that the order of G divides K. So in our case, the order of G is P to the M, and that divides R times P to the M minus 1. And the only way that can happen is if there's at least one P in R. So A to the P is G to the R, and this R has to be divisible by P. So let's write R as P times S, which is just a fancy way of saying that R is divisible by P. And now we take our G and we let B be G to the minus S times A. Now, B can't be in the cyclic group generated by G because if it were, if G to the minus SA were a power of G, then A would be a power of G. But A is not in the cyclic subgroup generated by G. So this element B is not in the cyclic subgroup generated by G. And if we compute B to the P, so in particular, it's not the identity, because if it were the identity, it would belong, the identity is in here. So B is not the identity. That's a special case of this fact. And what happens if we compute B to the P? Well, we get G to the minus PS A to the P, which is G to the minus PS G to the R, because A to the P was G to the R. But R is PS. So B to the P is the identity. In other words, B is an element in the group of order P, which is not in the cyclic subgroup generated by G. If you wanted to go back to the case of Z8 cross Z4, remember what G was. G was 1, 0. What is this H? H turns out to be 0, 2. It's an element which is not, well, I mean, this is one possible H. It's an element which is not in the cyclic subgroup generated by G, which is the things which have 0 in the second component. But it has order 2, because if you take H plus H, you get 0, 4, which is 0. So what we sort of did is we found an element in the other factor, even though we don't yet know that there are factors, but that's somehow what we found. Now, we have this subgroup H, which is generated by B. It has order P, because it's generated by an element of order P, and it doesn't meet the cyclic subgroup generated by G, because we know that B is not in that cyclic subgroup. Okay, now we're going to do the inductive step. So we're going to take this element G, and we're going to look at it in the factor group by this subgroup H. So if you're still using the Z8 cross Z4 example, what we're doing is we're modding out by H, and what that leaves us with is Z8 cross Z2. And our element, which was 1, 0, still has order 8 in this factor. And that's true in general, because let's compute here. Suppose we know that G has order a power of P, so GH must have order some power of P. I mean, the order of G mod H is still a power of P, so every coset has order a power of P. If GH to the P to the S is H in the factor group, that means that G to the P to the S is in H. But if G to the P to the S is in H, that means that G to the P to the S is in the intersection of the cyclic subgroup generated by G and H, which is the identity, which means that G to the P to the S is the identity, which means that P to the M must divide P to the S. In other words, the order has not gone down. Now we use some theory. So G mod H is a group, an abelian P group of order smaller than the original group. So we know that there's a subgroup K of this factor group, and that we can factor G mod H as this subgroup and the cyclic subgroup generated by G. That's the inductive hypothesis, that a smaller group has this factorization. How do we get back from this to a statement about G? Well, we consider J to be the collection of elements K in G with the property that KH is in K, which is a subgroup of G mod H. In other words, you take the preimage of this subgroup under the canonical homomorphism. J is a subgroup of G, so why is that true? Well, it's true because if K1 and K2 are in the preimage, then we just have to check that K1, K, so that means that K1H is in K and K2H is in K. But then K1 times K2H, which is equal to K1H, K2H in the factor group, is also in K, because K is a subgroup. So if you multiply two elements of it, it stays together. And similarly, if you check identity and inverse, you find that, that J is a subgroup, and it's a subgroup of G, and it contains H. Because if you happen to pick an element of H, then under the canonical homomorphism, it maps to the identity element, which is certainly in K, whatever it is. So we've now found a subgroup in G, which contains H. The next thing we know is that every element of G can be written as a product of a power of G times an element of K. So why is that true? So suppose we have an element U in G, an arbitrary element, and we look at its image under the canonical homomorphism. Then because in G mod H we have this product decomposition, we know that we can write UH as ZH times KH, where Z is an element of the cyclic subgroup, the image of the cyclic subgroup, and K is in this subgroup J. This is the decomposition of G mod H as GH cross K, which you could think of as J mod H. And what that means is that U is equal to Z times K times an element of H, because this is an identity of cosets. But if K is in J and H is in H, which is a subgroup of J, then KH is in J. And Z is in the cyclic subgroup generated by G. So this tells you that you can write U as a power of G times an element of J. The second thing you can observe is that if you look at the intersection of these two subgroups, so in other words, something which is both a power of G and maps to this subgroup K in the quotient group, if H is in here, that means, first of all, that H is in K. Remember that G mod H is the cyclic subgroup cross K. If you're in both under the canonical homomorphism, then means on the one hand you're in J, which means when you take the corresponding coset you end up in K, and on the other hand you're in G, so you end up in GH. So HH is in GH. But the intersection of these two it's in the intersection of K intersect GH, but that's just H. So the only way that and then so in other words, but we already know, so it means that if you are in both of these things, you have to be in H. But if you're in both of these things and in H, then you have to be the identity, because the only element of H which is in this group is the identity. So what we've finally shown is that we have two groups, two subgroups, the cyclic subgroup generated by G and this mysterious group J, which are contained in the group G. Their intersection is trivial, and together they generate the group. And that's exactly the situation of saying that G is the internal direct product of these two things, namely G is this isomorphic to the cyclic group, the product of these two things. And that's what we were trying to show. So we've successfully split off a factor. And if you go through this proof and you look back to my example of Z8 cross Z4, what you end up with is that J turns out to be this Z4, and the cyclic subgroup generated by 1, 0 turns out to be this Z8, and so you recover this product decomposition.